Hey folks, this is Answer Everywhere. And today, just like every day, we're taking a look at some source code that we've never seen before. Sort of like sight reading, like you see in music, but source code, instead of notes and stuff. So we're looking at the source code of AMD's ROCm software. ROCm is AMD's answer, or attempt to answer, to Nvidia CUDA. The source code for CUDA is not open source, and I wanted to learn a little bit more about GPUs, how they work inside, and all of that stuff, since GPUs are going to run our lives, Skynet style. And since I can't look at CUDA, which is the more popular one, I figured we would look at ROCm. I don't know entirely how this is laid out. They have like 6 trillion GitHub repositories, if I'm counting correctly. And each repository seems kind of small. So they're, to me, that's kind of madness. I know that's a popular style. So we'll have to sort of jump around to see where any of the real functionality is, because there are so many repositories. There's going to be a lot of overhead in the form of different doc directories, different DevOps directories, continuous integration, all of that stuff. So all of that, there's going to be a lot of repeating there. There's probably not going to be great tooling that allows us to jump from one repository to another. But we'll make do. We'll make do. And they do make charts. Let's see if I can pull up one of these ROCm charts. I think the main thing I want to see, at least first, is HIP. So the applications are for HPC, which is high performance computing, and machine learning. And they have different tools, including a debugger, which is nice to have. They support frameworks like there's like a ROCm version of PyTorch, and if you own an AMD device, then you will know that there's some friction involved in taking some like a well-known open source project that was built with CUDA. Often they'll add ROCm support. Sometimes that works well, sometimes that doesn't. Sometimes some upgrade breaks in a ROCm dependency and so forth. So for a lot of these frameworks like PyTorch, TensorFlow, there is a ROCm version that's maintained by AMD. And I think that mainly what they're doing is just updating those existing frameworks to use their ROCm stuff. But they also have this MI prefix. It seems to be AMD specific, but I'm not sure. But they have like this thing called MI Open. They have some MI Graph thing. They have some MI JPEG thing. I'm not sure entirely if that's AMD specific, but we might look at some of those. And then some of this stuff like BLAS is general purpose, but they again have their own AMD repo where they are kind of tying in whatever BLAS is doing with the like machine level code that their AMD stuff speaks, or at the very least using the ROCm layer as a middleware that compiles to both Nvidia and AMD machine code. And then RCCL is some communications library. I think probably ROCm communication library. I don't know if the C is the C in ROCm or if it's a different C. And then HIP, I think, is probably the main entry point that I've seen. So I think I'm going to start there. And then here's the fully open source ROCm platform. I guess we can look at that. We have that repo open, I think, but this mainly looked to me like build scripts. And then the theory is that it will run on multiple different devices, including CPU. So I don't know if you need to have a Radeon CPU, but in theory, I guess if you have both a GPU and a CPU, an APU should be basically a GPU optimized for AI. And I don't know what a DLA is. We'll look that up. But in theory, if you have these, you can run on this heterogeneous collection of devices. So if you have some LLM, it can both use GPU cores and CPU cores and APU cores. I don't know what DLA is. A deep learning accelerator. Okay, so it seems like another acronym that basically means a GPU-like thing that's optimized for probably fast linear algebra with lower precision than the GPU would be. Because often in AI, you can get along with using lower precision floats, which compute faster and cheaper than you can. Whereas in gaming applications, you often want better precision because you are not as concerned about resource usage. So anyway, that shows what I know. But let's dig into, I guess let's poke around the ROCm repo before we go on to HIP. And then maybe there's something here. There's licensing and stuff that's boring. That bores me. So there's tools and docs. Those are also boring, and we have CMake modules. So what really is here? I'm not sure. We have some auto tag and a ROCm build in tools. And we have headers and shell scripts. Are they all shell scripts, or are they also, there's some XML stuff. Overview for ROCm.mk. So this is going to build the various projects that make up ROCm. So I guess this seems to be like a repo that is essentially just what's the word? Like the, I guess, entry point is what I called it before, or I refer to something else as the entry point. But this is really just like, it's going to call a bunch of other stuff via shell scripts, and there's not really any substance here, I assume. And I'm not going to read bash. I'm not going to read some bash script that's supposed to compile on every piece of hardware because it'll be unreadable and unfollowable. But we have this like hipify, some Clang stuff, some blast stuff, and I'm going to guess these are all just going to pull in some other repository. I thought they were headers. They are not headers. I was reading the H at the end. I should have gone one letter before that to look at and see that it was a shell script. And then we just have this CMake file. So there's nothing here. I consider this repo a bust. We'll keep open, I guess, this. We can always find this JPG thing again, but can I pull this out and let's try moving it to its own workspace in the hinterland. All right, that brings us to HIP. I think HIP has real content. I think all of the content is headers because I looked at it before. So we include /HIP, which you can include if you want to be more hip. And we have hipify, which is going to automatically convert source from CUDA to HIP. So that's just their tool to probably essentially a sed or awk script to take identifiers in CUDA and map them onto whatever is the closest thing to HIP. Probably not literally a sed script. It probably has some intelligence. It might be something more like a C preprocessor. Okay, but other than that, we have include. We open that. Util, that's probably going to be mainly for the developers of HIP to maintain and do other stuff. But we also have Docker, which is they are going, because this stuff is frankly kind of hard to get working, the main way that they have of getting it working across platforms is typically they'll distribute like a Docker container. So you can get a TensorFlow Docker container and it will have all the tools that you need to run like a typical Python project that uses TensorFlow. Those projects, as I mentioned, are typically designed for Nvidia cards if they're AI or GPU aware at all. And so you need various tools and or libraries to make sure that they work on your AMD card. And I think that's getting that all correct and is much easier to do by providing a Docker container than by like providing instructions for all Windows, Mac. I don't know if Mac can even run these GPUs, but and all of the Linux distributions like Fedora and Ubuntu or whatever. So they just distribute these containers, and that's fine. Everything just passes through to the GPU. There's a little bit of overhead, but the GPU is doing all the work anyway, so there's not much overhead there. And then bin and CMake, I think are not going to be interesting. Bin has find HIP, which I guess will try to find where on your disk the HIP library is. And bin has what? A CMake linker helper. and a hip demangle ATP. ATP is what your cells make, and these are both bash scripts. I'm sure ATP is also something that is existing in computer world. Okay. So let's look at include hip. That's really all there is. So under util, we have just gedit and vim. Those are editors. These are going to be presumably settings for those editors to work with hip. Okay. And we have headers. Nothing but headers. And what is in them? We have things like channel descriptor, device functions, driver types, some hip floating point 16, floating point 8, GL interop. I'm guessing that's maybe OpenGL, HCC. Maybe that's like the hip C compiler. HCC is an open source optimizing C++ compiler for heterogeneous something. Heterogeneous compute. Okay. I'm going to guess it's kind of like a customized version of GCC. So let's just maybe open all of these. In fact, is that any easier on Emacs? I do have this open in Emacs. I also have a few of the other repos like migraphx. I mentioned the mi prefix, mi open, mi vision. I don't know what of those we'll get, in fact. And I didn't even clone the ROCm repo, which is what I thought I cloned. I mean, hip repo. Do I have hip? I don't have hip. Also, we'll do hip in the browser. And then if we need those other repos, we'll go there. Okay, so let's start at hip common. Hip complex might be complex numbers. BF16, those are like, I assume 16-bit floats, but they're also your best friend forever. I don't know what the BF is going to be. Driver types might be worth looking at. Before we get to BF, I think we should look at the floating point ones. I guess we'll look at HCC. Math constants is probably not so important, although I like math, so we can at least see what constants they care about. Profile, I'm going to guess is profiling, as in the sense of recording information about how performant the hip is. And the runtime seems probably important. The runtime API. We have texture types and vector types. Hip RTC. I don't know. That's not RPC. Remote Triton call? I don't know. We have math function. We'll just basically open everything. And the question is, do we start with hip common or hip runtime? I guess we'll start with hip common. It's 100 lines. That's almost nothing. Now it seems to be mostly macros, which makes sense. And we're using some Clang pragmas, which I am going to look at, because if everything is macros, I should take a little bit closer look than I usually do when I see a bunch of if defs. So if Clang is defined, we're going to, whatever Clang diagnostic pushes, presumably there's some stack somewhere that we're pushing diagnostic onto. I'm going to guess diagnostic is something like a flag saying that we're going to diagnose some stuff. Let me pull I'm just a little bit worried about my stream quality because it's been bad in the past. Just want to make sure that I see all the things I'm supposed to see on the left here. Okay, looks good. All right. And then whatever this is, this seems to be pushing some sort of flags, I would guess. And there's some common stuff, common code included at the start of every hip file. Auto enable hip platform AMD if compiling on AMD platform. So we're going to if and def hip platform AMD and so on and so forth. And auto enable hip platform Nvidia if compiling with Nvidia platform. Okay, so this is just setting up, I guess, on the in the hip files, whether we're doing Nvidia or AMD. And then we're going to define this hip public API. Only if we're in GNU-C. If we're not in GNU-C, I don't know what we do. Oh, I guess we do this. Okay, so this is the same defines, except I guess the GNU-C have these like, I don't know if these are like extensions or some sort of annotation that I guess makes sense in the GNU compiler, but not in other compilers. And then we've got some, we'll define some atomics. I guess we're defining these all as 0. Is that right? The global int32 atomics, atomics exchange, and so on and so forth. I don't know what these are really doing, though. Is it just creating the variable? Let's ask ChatGPT. ChatGPT will think and think and think. I guess I don't need to send this to O1. They seem to be feature flags for HIP's support of certain 32-bit atomic operations. Float atomic exchange, etc. By defining each feature flag to 0. The code is effectively telling the compiler / toolchain these features are disabled or unavailable on this architecture. I see. So in many GPU programming environments like CUDA, HIP, etc., macros like HIP arch has global int32 atomics are used inside if conditions to enable or disable code paths. Okay, so this is just setting them to 0 to disable them. But why? What if are we in? Oh, okay, so if HIP device compile is 0, I guess that probably is some sort of failure condition maybe. Then we don't have any of these features, I suppose. Which I guess they are concerned that they may have been added before, or maybe they just need to exist in order for HIP to run. HIP complex, I guessed this was the complex numbers. This is not the next thing I would do, but it's here. Let me just verify if I can get rid of it. AMD HIP complex. And there's nothing really here. It's just including some stuff. So here's BF, maybe this is all just includes. Include HIP / AMD detail, etc., etc. So where is this? Include / HIP. Can I find this file? Where are we including it from? It doesn't seem to be part of this this repo. So maybe this repo doesn't have anything. Where is the AMD detail folder? Or maybe it's created by the scripts. All right, so let's assume for a second that it's created by one of those scripts and look at the actual, so AMD HIP f8.h. Let's see if we can find this particular file, ignoring the directory. No. So where is it? It must eventually go on your thing. So let's try go back into the ROCm. The ROCm repo. It's GitHub. GitHub, your UI sucks, I have to say. All right, so let's look for this file. I'm gonna guess it's not in here. Let's look for AMD details. Was it AMD detail something? Where else could it be? Let's take a look at their repos. Triton, RDCode, etc. So here's the ROCm entry point. Here's composable kernel. Is it possibly in composable kernel? Here's some library for sparse linear algebra stuff. It's possibly in one of the lower level libraries, but I don't know about that. We have HIP tests, the validation suite. Maybe it's in the runtime. Let's take a quick look at the runtime. HSA runtime tools. PC's loader image. I don't know. What if we did a search for, what is it? Language. We have some OS stuff. What did we look for? Did we already look for AMD detail here? No. Okay. Let's just ask ChatGPT. So in ROCm, some files include AMD detail slash. Do we have an actual example? foo.h for some header. Where is the source code for these headers? ChatGPT is so slow. That's Gemini. Usually indicates that the header is part of a specific ROCm component. For example, HIP ROCm libraries. Download the source code for the relevant. Yeah, I'm asking what the component is though, man. HIP, AMD detail, various headers. They don't live in the HIP repository. Or at least they don't seem to. So let's pick, what was it, common? How about floating point? AMD HIP fp8.h. We only have FNUZ defs for now, which are not supported by other platforms. I don't know what FNUZ is. FNUZ. Okay, so HIP has two FP8 number representations called FP8-OCP and FP8-FNUZ. The Open Compute Project number definition can be found here. The FNUZ suffix means only finite and NaN values are supported, unlike other types. Inf are not supported. NaN is when sign bit is set and all other exponent and mantissa bits are 0. All other values are finite. I guess this is so that they don't have to use more bits to represent infinity, I would guess. The Open Compute Project. You can read this PDF and it will tell you, I guess, how to represent a float. It's too zoomed in, but this is all like header stuff. So these are some definition of a number. Okay, so that tells us what an FNUZ is. That does not tell you where this file is. Maybe it's in a different repo. AMD staging. Let's look at a specific ROCm release. How about, there's like, what are we on, like 6-ish? 6.1? Let's try 6.1.x. No? Let's try 6.0. Okay, I guess the .x repo is actually where I want to be. Fine. And let's see if this is any better. Again, we have include/hip. We've gotten rid of floating point 8, but everything else seems here. And again, we have these files. Let's try doing a Google search with site github.com. We see that it shows up in the GitHub issues. So does it just pull it from some... Maybe you have to like download the SDK. Maybe the source isn't really available. Is that possible? That doesn't seem possible. Can I search across all of GitHub for this file? So this person has the file hip include/hip /AMD detail. What is this? Tracing heterogeneous APIs. Okay, so this is maybe the file we're looking for, but include hip AMD detail. So some people have it. What is this? ROCm/CLR? Compute language runtimes. I guess this is where we want to be. This is the same ROCm, right? Okay. Finally. There is no indication that CLM was an interesting repository. Not in any of the documentation I've seen, nor in the repo itself. What was it? CLR? This is one of the many areas where it's like a bad idea to have a bunch of repos when one repo will do. Okay, so I'm guessing that this is really where the stuff is. AMD CLR, compute language runtimes. In fact, we're going to give this its own tab. It contains source codes for AMD's compute languages runtimes. I guess probably the person who wrote this is not a native English speaker. So it can for the HIP and OpenCL trademark. So OpenCL, I guess, is I don't know if they're competitors. OpenCL, the Open Computing Language, is a framework for writing programs that execute across heterogeneous platforms, consisting of CPUs, GPUs, digital signal processors, DSPs, etc., FPGAs, and hardware accelerators. I guess it is. I think I was maybe confusing it at first with OpenGL, which is graphics specific. Okay, so I guess we can maybe like compile from ROCm to OpenCL or something along those lines. HIP AMD contains implementation of the HIP language on AMD platforms. It's here. OpenCL contains the implementation of OpenCL on AMD platforms. It is hosted here. And Rockcooler contains compute runtime used in HIP and OpenCL. So this seems to be maybe something in common. Okay, finally, some source code. So we can either go with the C files or with the headers. I guess let's start it with the headers first, and let's look at some floats. And again, let's make it its own frame. So we'll look at floating 8, floating 16, whatever B floats are. and common and complex and some of the other stuff. Vector types, surface functions, I'm going to guess are for like two-dimensional surfaces. Warp sync, I don't know if that's about like synchronizing function calls and stuff. Concepts is interesting. Grid launch, presumably for running on grids of various devices. Hip assert, I'm going to guess it's just some assertion stuff for like writing assertions in code. Here's GCC support. A runtime profiler. Math forward, maybe just forward declarations. Program state, potentially for storing and restoring program state and stuff like that. Runtime PT, maybe runtime pointer. I don't know. Unsafe atomics. We'll look at a bunch of this stuff. Cooperative groups. And channel descriptors and device functions. Yeah, let's look at a bunch of this stuff. Okay, a bunch of if-defs, but I think we should probably have real code here. Yeah, so 2,933 lines. This is floating point 8. And we're in some internal namespace. We can cast something to F8. What are we casting? It's templated. And you pass in whether it's an fnuz, which we saw before. That's like a finite. I don't know what uz stands for, but you give it a WM and a WE, maybe modulus and exponent, and whether to clip, I guess. Stock is maybe stochastic, and some RNG. And I'm guessing the RNG is in case it's stochastic. I don't really know what that means, but maybe there's, when you cast to F8, maybe there's rounding, and that rounding can be randomized or something. And then we have some bools, like whether it's half, I'm guessing half precision, whether it's float, whether it's double. I think half is half of a float. And then we're going to do some static assert, saying that only half, float, and double can be cast to F8. And then we get the size of the type, and I guess that tells us whether something. So if the size of the type is 8, then we return 52. Why? I don't know. So 52 plus 8 is 60. I don't know if that means anything. Then we get the size of t, and if the size of t equals 4, we do another comparison and we return 23. Otherwise, we return 10. That's FMT. Maybe that's the size of the modulus. Due to the 53. A double float uses 64 bits. 64 bits in total. We did see 2 to the 52. Let me see if there's a diagram here. Yeah. Okay, here we go. So that's what's going on. The 52 comes from the fraction. I don't know what MFMT is, but whatever it is, we're figuring out what the fractional, how much of the bit, how many of the bits are used for the fractional part versus the exponent part versus the sign. And so it's 52 for double and 23 for float. That all checks out. So that's what's going on here. And then we've got this unsigned long x that we're gonna stuff something into. And if the size of t is 8, then it is a double, I guess. And we're going to reinterpret cast x or underscore x rather. Where did that come from? It's the thing that was passed in. I guess the type. No. It's a thing of type T. So that might be like in this case, a double. So we're going to reinterpret cast it as an unsigned long, I guess, just so we can think of it as a bunch of bits, and so on and so forth for float and half. And then we're going to create variables for the head and mantissa, and for the exponent and bias. I'm not really sure what the bias is. Exponent bias. In IEEE 754 floating point numbers, the exponent is biased in the engineering sense of the word. The value stored is offset from the actual value by the exponent bias. Biasing is done because exponents have to be signed values in order to be able to represent both tiny and huge values, but 2's complement, the usual representation for signed values, would make the comparison harder. Oh, I missed a chat. Hello, Koorosh. I don't know when you wrote that, but I apologize. I apologize for not getting back to you sooner. Okay, so I still don't know what this bias is. So it's I understand what it's saying here. Hello, they're still here. Welcome. I still don't know what the bias is. Something about you can't store it in 2's complement. That makes sense. The exponent is stored as an unsigned value, which is suitable for comparison, but when interpreted, it is converted into an exponent within a signed range by subtracting the bias. Okay. So if there are e bits in the exponent, the bias is typically set as b equals 2 to the e minus 1 minus 1. Therefore, the possible integer values that the biased exponent can express lie in the range, the closed interval, from 1 minus b to b. To understand this range, with e bits in the exponent, the possible unsigned integers lie in the range 0 to 2 to the e minus 1. However, the strings containing all zeros and all ones are reversed, or rather reserved for special values. So the expressible integers lie in the range 1, 2 to the e minus 2. Okay, so that makes sense. We just have a thing that we subtract to deal with the fact that we're not, strings of bits are not perfect representations for numbers. And that's just some detail you have to think about when you implement a floating point library, as they are doing here. Okay, so they have some bias, which in the case of, I think I've convinced myself that size of t equals 8 means we're dealing with doubles. The bias there is 1023. And so on and so forth. That's 1024 minus 1. And 127 is 128 minus 1, and so on. And then we get all the stuff that we need to create the float, like the head, the mantissa, the exponent, the sign, the bias. F_inf is maybe just how how infinity is encoded in that type, and so on. And then we'll set signed inf to 0, nan to 0. If we're in fnuz, then if we're clipping, we're going to take sign left shift 7 plus this constant. Otherwise, we're going to return OX80. That's going to be signed infinity. And I guess that's why? I thought fnuz had no signed infinity, but maybe I'm not sure. So I think it does have a nan. I'm not sure exactly what's going on here. Maybe we have to define some signed infinity because the fnuz doesn't already have one or something like that. And then if we equals 4, I don't know where we came from, but whatever it is, if it equals 4, then I think EF4M3 is maybe some standard for floats. No? Float stored in 8 bits. First one is E4M3, 1 bit for the sign, 4 bits for the exponents, and so on. Okay, so there's some standard for an 8-bit float, and I guess we're employing that standard with whatever the clipping is. I don't think we've seen what the RNG is for. Hey, thanks, Friction. I appreciate that. I spent so long looking for a file. It's feeling a little bit gloomy about whether this stream would turn around, but I really appreciate that. So here's the first mention of RNG. Add RNG to Mantissa and truncate for stochastic rounding. Okay, so that's exactly what we're doing. So there's stochastic rounding. That's, I think, familiar to people. I think maybe in like chemistry somewhere, there's a standard rounding rule that if it's below 5, it gets rounded down. If it's above 5, it gets rounded up. If it's exactly 5, I figure what happens. You might flip a coin or something. Or it depends. It'll depend on the next digit if you have more digits, but I think that's really what it's for. Okay, and so this is just some implementation of floating point 8. And what is the AMD specific stuff here? I guess we have some calls here to built-in AMD GCN CVT, SR, FP8, F32. Maybe that's hardware support for some of these conversions. Built-in more stuff. GCN, I don't know what that is. Let's maybe just search for that in ChatGPT. They should have a better search system. Yeah, I agree. The search system is not bad. I think the reason they don't offer better search is just because it's expensive, is my guess. It would be expensive to index all of those repos, and so many repos are not worth indexing. They're like some person made them 10 years ago and have abandoned them. Okay. It's a Clang/LLVM compiler built in for AMD GPUs. The AMD's GCN target. I don't know what CN stands for. It computes the median of 3 single precision floating point values. Okay, floating median, I'm guessing 3F. Okay, so it returns the middle value by magnitude, et cetera, et cetera. Under the hood, it directly maps to the AMD GCN hardware instruction for floating point median of 3, often called VMED3F32. Okay, so what is AMD GCN? I'm guessing that's just the graphics core next. So that's just some like marketing code name for the I guess current generation of graphics hardware from AMD rather. Okay. So that gives us a flavor. We're calling ultimately these built-ins. And then there's a bunch of other stuff we're doing that's just regular moving bits around in C code. And then eventually we figure out what kind of float we're dealing with and we call some AMD instruction. And that makes sense. That's good. Floating point 16, I'm going to guess, is more or less the same. We've got this half stuff. It's a creator. I don't know what a creator is. I assume it means like constructor. And what are we doing? We've got some volatile stuff. So the underscore half and this is a class. The class is half, right? That must be what's going on. We have half to raw is some struct. Somewhere there should be a class. Or struct. Oh, okay, half raw and half to raw. And here's the half struct. And a half struct is a union of float 16 data, or rather some float 16 stuff and an unsigned int or unsigned short, which is called underscore x. And I guess this is either thinking of Why is it a union? So if the size of float 16 is the size of unsigned short, we're static asserting this, that these are the same size. And so these contain the same information, I guess, just in different formats. And this is some convenience class, I think, to figure out if they're the same stuff. So for example, the equal operator, if you pass it in a half raw x, then we're going to check if the data are the same. Oh no, this is assignment equals. So we'll just override the data. But that doesn't seem to do anything to the underscore x thing. But I guess we have a union so that we only need to do one of them. And then so on and so forth. Do we have operator equal equal? We can increment. We'll just increment data and so on. So I'm not really sure what this half thing is doing. It's sort of a convenience thing that seems to be mostly a float 16. And I'm going to ignore it. Here's bfloat. I'm just curious what bfloat stands for. Provide support for HIP bfloat 16. If this is a C compiler, blah, blah, blah. 0 extend lower 16 bits of bfloat. Maybe we'll just do a Google search. Bfloat. Bfloat, or a brain, whoa. A brain floating point. Is this real? Is a computer number format occupying 16 bits in computed memory. It represents a wide dynamic range of numeric values by using a floating radix point. This format is a shortened 16-bit version of the 32-bit IEEE 745 single precision floating point format, binary 32. Let's look at bfloat 32 then. We'll add this to Wallabag so I can read about it later. What? Why do we have bfloat 16 and not bfloat 32? Is that not a thing? So we have half. All right, so let's look at, this is just single precision float. Okay, that's just a standard float, 32-bit float. And I guess that bfloat is like a, instead of having like a, well, why a brain? And it's not to be confused with a binary 16, a different 16-bit floating point number. So this, I think, is binary 16. This is the, I guess, the standard half precision. And then bfloat is just some other way of throwing away data. So the bits are laid out as follows. Here's a half precision float. This is, I think, what the standard half is. You've got 1 bit for sign, 5 bits for exponent, and 10 bits for fraction. And in bfloat 16, we just take what? We just take what? 3 bits from the fraction and give them to the exponent. And then Nvidia has a tensor float 32, which is 19 bits, which has 1 sign, 8 bits for exponent, just like bfloat 16, but its fraction is 10 bits. And then AMD has a similar thing, except for some reason, their fraction is 6 bits larger and the exponent is 1 bit shorter. And then Pixar also has its own thing, because Pixar, I guess, probably worked all this out in the 90s when nobody else really cared as much. And they decided to go with an 8-bit exponent and a 15-bit fraction. And there's just more. Okay. This reminds me of a paper I read recently. This addition is all you need for energy efficient language models. And their idea is that since integer operations are so much faster than floating point operations, that they're going to emulate floating point with addition. And I forget what they do. But basically, They just use integer stuff, and that's some approximation. And it's, again, for AI, a lot of the stuff is like nearly as good. And they claim that it'll save money and energy and all that stuff. I forget. I think that maybe this is their stuff on the right-hand side. Or no, these look like the standards. U4, M3. I'm not sure, but you can read this paper. Edition is all you need. One of the many papers in the Blank is all you need series about LLMs. Okay, so this is floating point stuff. We're going to move on from floating point and see what else. HIP common, it has nothing. We're to find some stuff about Clang only. We're still in AMD detail, which is what I wanted to check. Complex. My only question is this complex numbers? We're including CMath and math.h, which is suggestive. And we have HIP C real, HIP C imaginary. So these are the real and imaginary parts of complex numbers. And this is the header. But I assume if we found our way to the implementation, we would see some calls to hardware routines. Just for the sake of fun, let's find complex. Maybe the calls are actually in the header. What is it, AMD GCN? I don't know. We're including vector types. I don't know if we're doing any hardware stuff. This might all be just done in C. We have things like make HIP double complex. Is that... Well, no. Come on. Yeah, so double complex is just double 2. So I'm guessing, I don't know really what is HIP specific about any of this, but it's something. So Friction is asking me, which language I have most experience and enjoy coding in? I don't know. I feel like maybe C++. But I did almost all my C++ at Google, and the C++ development at Google is very Google specific. So a lot of the libraries that we use there are not used in the wild. A lot of stuff that you can do with C or C++, you are not allowed to do, exceptions being the most famous one. Or maybe you're allowed to do them, but only if you're writing the low-level libraries. I found that, for whatever reason, I found that a natural environment to work in. But, you know, I've never, so far I feel like I haven't found a language that is the most natural to me. They all feel like they have bits and pieces that I enjoy, but not yet the language itself. I'm thinking Haskell is maybe getting there. The main weakness I see with Haskell is the tooling, which isn't technically a problem of the language itself. I thought Java and Kotlin had really good tooling. Python I used to like a lot, but I've grown. I like it less and less. I don't know why. And then R I like a lot. I've enjoyed R. Okay, so this is the vector types. These are just types. And what do we have? So these are just templates. We have things like we can test whether something is integral. For example, I guess an unsigned car is integral in the sense that we can maybe convert it. Have I ever gotten into the Lispy side? I haven't. And that's not intentional. I guess first of all, Emacs is the Emacs Lisp is weird because they have because of how it handles scope. But my my attitude was, and to some extent still is, that I want to learn Lisp, but I'm thinking of Lisp as essentially an untyped lambda calculus, and I'm thinking of Haskell as more one of the typed lambda calculus variants. And I like types a lot. So I think that when I do eventually get into Lisp, if I do, it'll be like kind of after I've explored Haskell a bit. I feel like I've done some Lisp. I think I've worked through like the Little Lisper book or whatever that book is called. And I enjoy it. I just, it's very powerful and doesn't have types. And that's kind of the same issue that I have with like things like Python and JavaScript. As they get more powerful, it's easier to write buggy codes that you don't know are buggy until you like hit some corner case at runtime. And I find that kind of unpleasant to debug and understand. And so that's a big reason why I enjoy the experience of types a lot more. Speaking of types, this vector type stuff, this doesn't seem so interesting. It's telling us a little bit about how HIP is thinking about things. But we've got, for example, this vector3, I guess, comparison operator. And here's the operator, equals equals. And you're just going to compare the components. So that's that. But I am curious about friction and Koorosh and anyone else. What your experience is, and whether you have a favorite language or if you've played around with Lisp. I feel like Lisp is like the Lisp is like the most different common language that there is. Everything is kind of a descendant of C or a descendant of Lisp, and those are the two like fundamental types of languages. Okay, so this vector stuff is kind of just doing what I thought it would. It's kind of, it was interesting to know what was in here. Now this makes sense, but we're going to move on. Surface functions, I think it's going to be stuff about like two-dimensional surfaces. I'm not sure, but we'll see. CUDA is using byte address need map to pixel address for HIP. Okay, so whatever a pixel address is, I guess to the coordinates for some pixel. And I don't really know what we're doing. Some image stuff. HSA Xed image channel type unsigned int 8 is equal to 11. S norm int 8. So this is an LUT. That's something. That's something I recognize from like working with images. I think color spaces. Maybe something LU factorization. Maybe something transform. LUT, a segment of YouTube channel Vsauce. LUT, a tributary of the river Mureș in Transylvania, Romania, where Dracula lives. A lookup table. Oh, maybe it's just lookup table. What am I thinking of? A 3D lookup table in image processing. In film and graphics industries, 3D lookup tables, 3D LUTs, are used for color grading and for mapping one color space to another. They are commonly used to calculate preview colors for a monitor or a digital projector of how an image will be reproduced on another display device, typically the final digitally projected or release print of a movie. So I guess this is essentially a simulation of some other monitor. And you have, for each color or something, you have the corresponding color. Red, green, blue, 16-bit lookup table, example. I'm not really sure how they work, but that I assume this is this sort of lookup table we're talking about here. I don't know what any of these things are. I could look them up individually. I assume they're part of maybe some standard, but I'm going to ask ChatGPT. What's up with this? So Koorosh is saying they personally really enjoy Scheme in C, yeah, but strongly disagree that debugging untyped code is really hard. Wish there was a type scheme with all the nice bells and whistles. Yeah, so when I say I don't like to debug it, I mean a lot of the bugs you can't know about until you run the code. Whereas the idea of types is like there's a type checking / compiling step where you verify that like all of the functions are well defined in a sense. And with something like Lisp, it's not you can pass in like things that wouldn't type in a typed language, and that's a whole class of bugs that are harder to figure out. There's some like, for example, there's potentially a what's the word? Like an arbitrary code execution vulnerability in Emacs due to the fact that Emacs macros can, I think, just do arbitrary can execute arbitrary Lisp, and that's something that I don't think is widely known. It's not necessarily obvious. People have kind of known about it for a while, but it's not clear what to do or even how to check that like your package is vulnerable to it. And that's the sort of thing where because like the code that you write looks like the code that's executing and everything is kind of a Lisp, there's just not enough structure to write policy, certain kinds of policy elegantly, I guess is how you might think of it. And that's a thing that I got a lot from studying math. People often think of structure as something that's like bad, or that less structure is more freeing. But a lot of times structure is what gives you the nice properties, I guess. So Friction is saying they don't think they've used Lisp. Yeah. I think the learning by building approach is really good. I think it's good to do both. That's been my position on this channel, that there's the learning by doing versus learning by school. A lot of, like, for example, a lot of trades, like, I don't know, plumbing, you want to take some courses in plumbing before you start doing it. Whereas like you could be like, you could try to learn only through apprenticeship, but then when you saw some new kind of pipe or some old kind of pipe, you might not know what to do with it. And I think the same is true for almost all trades, that you need some combination of like a hands-on apprenticeship, but also some studying of the background material. And I think that people kind of tend to gravitate toward one of those approaches or another just based on personality. And there are distinct ways of getting stuck depending on which of those personalities you have. So my position, at least the past few years or so, is that you kind of have to figure out which one of those you are and like force yourself to try a little bit of the other way. And that'll often kind of open up new possibilities that you hadn't seen before. Okay, so back to the code for a second. Define some enum. Yeah, we do that. For the various channels in an HSA heterogeneous system architecture extension image. The name HSA-X image channel type T reflects it's a kind of type used for describing how pixel data in an image is represented, whether it's signed, unsigned, normalized, etc. Okay, so there's, for example, you could be assigned normalized 8-bit integer per channel. Okay, so these are just different ways that you could have an image. These definitions map directly to how image data is stored and used in GPU kernels. When HSM or ROCm code deals with images, it needs to know the type of each channel, size, etc. Okay, so this is just some sizing and typing information that you can, I guess, sort of like metadata for like, here's a bunch of bits. How should the GPU interpret them? Okay, so that's the enum. We have some whatever order lookup table is, something about the order. We see Surf 1 Dread. Surf Dread, I think, would be a good movie. I'm guessing Surf is surface. 1 is, I have no idea. 1D and read. Okay. So we have some, is text surf channel type. So I'm guessing this is like some texture surface. I think probably a texture is typically like a square, although there can be maybe like topological data associated with it. So I'm guessing that we're basically reading a square's worth of data, basically an array, and treating it as a texture surface or something along those lines. HIF surface object T. Let's see if we can find this type. So clicking around the documentation, it's just this thing. It's a pointer to a __ hip surface, which is what? And then the surface, I guess, can possibly have boundary. And I don't know what boundary mode 0 is. But you can also like clamp or trap. And I don't know what those things mean. Different ways of handling the boundary. I don't know if those are intersections. What are these boundary modes? Have I ever tried programming in pure binary? I don't know what that means. Like assembly or something else. I've done like a little bit of assembly in HIP. The boundary modes define how out of bounds texture or surface accesses are handled. Okay, so this is for out of bounds as opposed to the boundary of the surface itself. So for example, if out of bounds might return 0, out of bounds might cause a trap, for example, like an exception in Python, or you could clamp the coordinates. No, I have not. Have you? I mean, that would have to be done, I guess, as like I'm not sure what you're saying, but if you're like talking about like writing literal machine instructions in pure binary, I have not. Oh, cool. Was this on an ordinary computer, or was it like on a like an emulator thing? I know that they make what are they called? They're like machine emulators that they use for teaching assembly and stuff. Okay, so I don't know. So this is like surface cube stuff, layered right, etc., etc. These are just surface objects with X, Y, and face. We've seen like similar stuff, I guess, in gaming libraries. I'm not sure what we're going to really get out of digging more in. I was just kind of curious what this was. I don't know what OCL is, though. We'll look up OCL image store LOD CM. I'm guessing LOD is load. CM, I don't know. Image store. They took the time to spell all these words, so that I think that's just that part is clear. And then whatever OCL is. This Kronos thing. I don't think it's actually looking for what I told it to look for. DuckDuckGo. OpenCL kernel. Yes. Almost certainly. Okay. So this is OpenCL kernel, image store, LODCM, something. So some called it the OpenCL kernel stuff, I think. Let's just plow along here. I don't know what warp sync is. Warp sync built-ins. I guess I just kind of want to know what warp is. AMD warp. I think this is some AMD tooling. There's a video warp. Warp size is the number of threads in a warp. Video warp processor. That's a different thing, I think. Hex editor. Oh yeah, sure. I have worked in pure binary in that sense. Okay, so threads are executed in groupings called warps. Okay, so it's some collection of threads. I think warp is maybe a pun on sewing, whatever it's called. Like warp and waif or whatever. Weft. Warp and weft. Okay, so something about threads. Yeah, so you can, yeah, I've implemented like math routines in binary and stuff. There's also, no, this is not the one I'm thinking of. There's some of these esoteric programming languages like brainfuck and white space. White space is it's probably a fun language to learn. Here's an example. This is hello world. I think this top hop might be a comment. I think the rest is like the tabs and spaces that give you the control flow. And here's a brainfuck program. But I thought there was some more binary one, but if there is, it's slipping my mind. Okay, so this warp stuff I think is something about threads. Read first lane. I guess lane is maybe some physical part of the GPU. So Koorosh is saying that they have some docs for the GPUs where they give exact definitions for wavefronts and probably warps. That makes sense. I think I've seen that before. This looks like it's designed in the 1980s. Advanced chipset design. Everything looks like it's all lasers. I'm just gonna like randomly click. Here's some AMD Radeon thing. I don't know if this is going to be useful. We've got a branch and message unit. I guess top here, we've got some vector registers, which are 4 by 64 kilobytes. Some local data share. And scheduler. Vector units, which are 4 by SIMD16. A scalar unit, which looks pretty massive. Some scalar registers. Some texture filter units, of which there are 4. Texture, fetch, load, and cache, and L1 cache. But I think that there's other stuff. I don't remember how it goes. Maybe we'll just add the warp here. I don't know if any of this is going to be useful. Here's the memory system. For something. I don't know. It's possible that DuckDuckGo is just ignoring my stuff. So this has some, does this have anything warpy in it? All threads are I think this is where I was before. All threads are executed in groupings called warps. The amount of threads making up a warp is architecture dependent. On AMD GPUs, the warp size is commonly 64 threads. So it's some grouping of 64 threads, except in RDNA architectures, which utilize a warp size of 32 or 64 respectively. Respectively, there's only one thing in this clause. The warp size of supported AMD GPUs is listed in the accelerator and GPU hardware specifications. Nvidia GPUs have a warp size of 32. So in contrast to CPUs, GPUs do not generally employ complex cache structures or control logic, like branch prediction, etc., etc. Context switching between warps residing on CU, I don't know, CU is something, incurs no overhead, as the context for the warps is stored on the CU and does not need to be fetched from memory. If there are not enough free registers to accommodate all warps of a block, the block cannot be scheduled to that CU and has to wait until other blocks finish execution. So CU is maybe something like a core compute unit. Okay, so a compute unit has some vector caches. You could stuff some vectors in there, if you use them frequently. A vector ALU, accelerated something unit, presumably. A vector register file, where I guess store data, like register stuff. And these are the different SIMD units. And then we have a scalar unit. And the SIMD units are going to process the same instructions over a bunch of data. And then there's a local data share. You can all share your data. Compute unit, thank you. Let's look up ALU. Arithmetic logic unit, maybe? And let's pull up some, like a diagram or something for SIMD. A type of parallel processing in Flynn's taxonomy. So in SIMD, you have some instruction pool, a vector unit, and a data pool. This is basically what we saw. Do we not get another diagram? They exploit data level parallelism, but not concurrency. Each hardware element, PU, working on an individual data item sometimes also refers to blah, blah, blah. That sentence, I think, is not grammatically correct. But my understanding is you have some instructions and a bunch of different data. Like, for example, color this triangle red. And then your GPU has all of the triangles on screen, and it will color them all red, just essentially iterating in a for loop over the different vectors, but at hardware level. And the reason they have them in GPUs is, I think, precisely because everything is batch processing on triangles to some extent. All right, at any rate, this is some warp stuff, some warp sync. So warp, now we know, is some batch of threads. I guess these sync functions are for presumably synchronizing the warp stuff, maybe synchronizing the threads within the warp, maybe synchronizing the warps. But we have things like we're going to read the first lane. In theory, behavior is undefined when reading from a union member other than the member that was last assigned to. But it works in practice, oh Lord, because we rely on the compiler to do the reasonable thing. It seems like a source of potentially hard to debug bugs. Is this even defined compiler behavior? So this is basically saying they rely on undefined compiler behavior, it sounds like. And they use some macro to expand each built-in into a waterfall that implements mask semantics. The mask argument may be divergent. Each active thread must have its own bit set and its own mask value. For a given mask value, all threads that are mentioned in the mask must execute the same static instance. I don't know what all of that means, but we implement this as a waterfall loop that executes the built-in for each subset separately. The return value is a divergent value across the active threads. A divergent value across the active threads. I don't know what that means. The value for inactive threads is defined by each built-in separately. I don't know what divergent value is, but this is something where they're going to loop over a bunch of threads in a waterfall fashion. That's really all I got out of it. Concept says really nothing. Grid launch. This should be some sort of grid launching. We have a three-dimensional structures for groups and grids. I think it's three-dimensional not for the same reasons that... I don't think it's three-dimensional because we live in 3D space. Although, I know you never know. It seems like it has X, Y, and Z. GL dim 3. Maybe it is. Yes, this... but it's some like... either point in space or group of points in space to be used, I guess, for groups and grids, whatever groups and grids are. We have some GL barrier bit. I'm guessing that's the same sort of GL as in OpenGL. And you can we've got, I guess you can queue. There can be maybe no barrier and like a weight barrier, something like that. Grid launch parm contains information used to launch the kernel. So you have some dimension of the grid. Oh, you know what? I'm guessing that maybe this is for like the grid itself is three-dimensional. So maybe you have like a rack of machines, like accelerators, and you might have multiple racks. Are those the 3 dimensions we're talking about? So you might have accelerator 1, accelerator 2, accelerator 3, 4, 5, 6, and that's one unit with its own power supply or whatever. And then behind that is another unit. I guess that's probably what they're talking about. And then you can launch some stuff. It needs to know the grid dimensions. Whatever dynamic group mem bytes is, amount of dynamic group memory to use with the kernel launch. So I guess these, I assume we're talking about devices, a grid of devices. I'm still not sure, but maybe they can share memories in addition to the amount used statically in the kernel. And so on. A value of packet fences to apply to launch. They correspond to the value of bits 9 to 14 in the AQL packet. I have no idea. Let's take a look at... I think this is for like data center people, basically. In AMD's cooperative groups thread model, a grid is a single dispatch of kernels for execution. Maybe this is in a single card. The grid hierarchy and block hierarchy are thread hierarchy abstractions of cooperative groups. Defense grid, blah, blah, blah. Do we have any images? Let's just try AMD grid. In the context of if-else blocks being compiled on GPUs. I'll look up divergent value. Let's also look up ROCm grid. So ROCm does support high performance computing. And grid. So there's some grid library. Grid is a library for lattice QC. That's quantum mechanics. Let's ask what's up with the grid launch. And let's start a new chat. And let's get rid of O1. It's just too slow. In AMD ROCm, what is grid launch? Grid launch refers to a programming model used for managing and launching kernels on GPUs. It is an abstraction that simplifies the process of mapping computation tasks to GPU threads across multiple dimensions. A grid is a multiple of blocks. Each block contains multiple threads. They are executed in parallel. Okay. So you have some grid size 16 by 16 and block size 32 by 32. It specifies the number of blocks in the grid, the number of threads in each block. Why it's important. It enables scalability by dividing the problem into smaller tasks, simplifies programming by abstracting low-level thread management, etc. So if grid size is 16 by 16, is that subcomponents of a single device, or is it okay. Yeah, I think that's right. They do have to, yeah. Okay, so divergent value means what? That they've computed both branches and only one is valid, I guess, or something along those lines. Okay, so grid size 16 by 16 refers to logical organization of threads in a single GPU device. Okay. But what's a block? Along the X dimension of 60 blocks, each block is further divided into threads specified by block size. Okay. So I guess the thread is the unit here. Okay. So grid is some combination of threads to be executed. And where's the block size? So I'll ask, what is a block? A block is a basic unit of execution in the hierarchical thread organization for parallel programming of GPUs. So each block contains multiple threads, which are the smallest unit of execution. All right, so the thread is the unit, a block is a group of threads, a grid is some collection of blocks. So a grid consists of multiple blocks which are identified by block IDX, X, Y, and Z. Threads within blocks execute in parallel. Threads within blocks execute. So each block is like a unit of a parallel batch, and blocks themselves can execute independently or concurrently. Okay. And then there's an error in input stream. Okay, so that kind of makes sense. I assume that somehow, so I'll ask, relate this grid block and thread stuff to the physical hardware, such as SIMD or other components of the GPU. I just kind of want to get a sense of how this relates. So it's composed of multiple compute units, which we saw inside each CU. Inside each compute unit, SIMD units execute instructions on multiple data points in parallel. Then there are registers, local memory, and shared memory. A thread is the smallest unit of execution and corresponds to a single lane in a SIMD unit. Okay. I don't know what a SIMD lane is. Do we know that yet? Is that just the obvious thing? Threads within a block are grouped into wavefronts or warps. Okay, I guess warp is CUDA and wavefronts are AMD. A wavefront consists of 64 threads. All threads in a wavefront execute the same instruction simultaneously on different data. That's a thread. All threads in the wavefront. So an instruction is, we'll assume for now that an instruction corresponds one-to-one with a thread. That's probably not true exactly. But threads, I'll think of as instructions. Then a block is a group of threads, and they're distributed across different wavefronts. All threads in a block can share memory, which resides in the same CU and is accessible by all threads in the block. So these blocks are kind of like CU level stuff, and the threads are kind of like SIMD level stuff. A grid is composed of multiple blocks. Blocks are distributed across CUs. Each CU handles blah, blah. Each CU contains SIMD units that execute wavefronts in lockstep. If it has 64 threads and the SIMD width is 16, the wavefront is executed in 4 cycles. Okay. So I'll ask, is it more or less the case that block corresponds to CU and thread corresponds to SIMD granularity? Okay, so they say that's more or less a reasonable mental model. Why is the grid type 3-dimensional instead of 2D? Is it 2 dimensions for each block and then 1 dimension for the thread? So compatibility with 3D data structures, many computational problems inherently involve 3-dimensional data, etc. I don't think you really understood the question. For linear problems, you have n11, where n is the number of elements. For 2D problems, you have rows, columns, and 1 for matrix multiplication. Okay, I guess this, the 1 is just like a placeholder. Oh, okay. So the 3 dimensions really do correspond to like the dimensionality of like the tensors or matrices or whatever. Okay, and then I'll ask, what does it mean for a value to be divergent? And hopefully it will just know by context that I mean GPU. Situations in which different threads in a wavefront or warp follow different execution paths, such as taking different branches, which is exactly what Koorosh was saying. It is called control flow divergence, and it has important implications for performance. So a divergent value is a value that differs across threads in the same wavefront or warp. Okay. Causes those threads to execute in different paths. Okay, maybe it means, I don't know if it's referring to encoding the different paths in the vector somehow. Blah, blah, blah. So conditional statements for control flow divergence. If thread ID x is a multiple of 2, then we'll set value to 10. Otherwise, we'll set it to 20. In this case, the even threads execute on one branch while others execute on the alternate branch. The SIMD units must serialize these branches, executing one at a time, which decreases performance, and so on. These are like performance implications of how to do it. Okay, so at any rate, that's what divergence is. It's kind of like the control flow mapped onto the SIMD world. Is how I'll think about it. Okay, so grids, I find too confusing, but some way of mapping things onto control units and SIMD lanes or whatever. Here's program state. I'm guessing this is just kind of storing stuff. So we've got some kernel arg. Maybe these are like the arguments of the kernel. Kernel args size align program state impl. This is just, I guess, storing some stuff about the like pointers in alignment maybe. And we can get program state. So the program state class has a kernel descriptor, which has a pointer
And whatever an HSA agent is, that might be kind of like a device. It might be something else. We have this load executable where we can pass it presumably the name, maybe location on disk where the executable is, like a path, the size. I don't know, size of maybe the string, perhaps. The type of the executable, I guess, or rather some manifestation of the executable and the agent. And we can load an executable without copying. This might be something like loading into the GPU itself, whatever the program is, something along those lines. I don't know. Here's hip runtime, PT. I don't know what this is. We have things like memcopy, memset, and we're kind of mapping it onto the presumably we're kind of mapping on some of the code stuff into some of the strings that you use in the code to their implementations. And these are things like launch kernel, event APIs. We've been here for a while, an hour and 45 minutes. I think I'm getting pretty tired of looking at this code, but let's see if we can find anything especially interesting. I'm getting a sense of like where some of this stuff is. Now this is like launch kernel stuff. Unsafe atomics. So this is the repo, this CLR repo where they're implementing, I guess, the layer between like the C code and the hardware implementation. Like this hip atomic compare exchange strong is maybe one of the built-in methods in the GPUs or something along those lines. But let's see if we can see anything else from some of their other repos. I don't know about Rockel. Here's the hip repo. We decided is basically just glue. It doesn't have any anything interesting on its own, it seems like. What about RCCL? I don't know if that's cool. I guess source. We have like communication channels. I guess communication channels, a clique manager. Clique common. I don't know what kind of clique this is. So there's some GPU barrier that's shared across GPUs. There's a global sense, or rather the count is shared across GPUs. There's a sense, whatever that is, it's shared across GPUs, and there's a local sense which is shared, which is local to this GPU. So this some clique. I'm guessing a clique of GPUs. As in like a group of them that are all connected. Thank you. Satan W. Ortiz says, this is the best channel ever. I appreciate that. So in channel, this is some GPU channel. And I'm guessing RCCL must be, it's like some communication language, but I'm guessing that it's for the GPUs to communicate with each other. Now that we've seen the clique thing. True. Thank you, Koorosh. You seem to have all the answers about AMD. I'm so glad you're here. Okay, so init channel is going to initiate some communication channel. We're in the CC file as opposed to the header, which is good. I'm tired of reading headers. But where did channel go? What? Did I close it? I must have closed it. Okay. So initialize whatever NCCL com star is, some pointer to some handle, I guess, for communication. And we also have a channel ID. And then we're going to look in com at its channels some sort of hash table, and we're going to pass in the channel ID, and that's going to give us the channel itself. And if the channel ID is not -1, then we return success that we've, I guess, initialized it. If the channel ID is -1, then we're going to look in COM and get whatever n ranks is, some kind of rank, number of ranks, maybe like rank in file, and whatever VLS rank is. We're going to look at the cliques, whatever this test is doing. We might return the clique size, or we might return local ranks, and a bunch of other stuff I've never heard of. So CallNet and NVLS. This is some maybe HPC stuff. Let's look it up. CallNet, NVLS. Number of, is it an LVS? Number of levels? No. Number of virtual lab school, infants and toddlers. Yeah, I don't know. COLLnet. Did I misspell it? COLLnet. What is CallNet? Nvidia. Okay, so this is Mellanox. CallNet is a new algorithm in NCCL that allows GPUs on multiple nodes to do in-network reductions. Okay. Some sort of network stuff with GPUs. I don't really, frankly, know how it works. I guess, I don't know if the GPUs have their own network hardware, or if they have to be attached to a host that does the communication. I know that Nvidia, for example, makes their own network cards. I think they bought Mellanox. How do you spell it? Mellanox. Mellanox Technologies. It's Israeli. An Israeli-American multinational supplier of computer networking products based on InfiniBand. They offered adapters, switches, software, cables, and blah, 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 blah. Nvidia announced its intent to acquire the company for $6.9 billion. Okay, so they are owned now by Nvidia. And I think they make like super high-end network cards. Is that the only thing they make? Networking products. Okay, so Nvidia makes these network cards. I don't really know if they somehow bypass the kernel and allow the GPUs to talk directly. Maybe that's in the works. Maybe it exists. But somehow, CallNet is, I guess, supported by whatever this protocol is. And I don't know what the NVLS ranks will be. Let's just take this whole thing and ask ChatGPT about the abbreviations. What do some of the abbreviations here mean? Go. Is this Gemini? All right, so NCCL is NVIDIA Collective Communications Library. That's what a bunch of these stuff are. What is NVLS? It says you match, but where are the matches? Gemini. So NVLS is the NVLink Sharp. It's a hardware accelerated feature available on third generation NVIDIA NV switch systems, which significantly boosts the performance of certain NCCL operations. Okay, so what is this? So whatever this communication stuff is, it is essentially, it seems like it's implementing whatever NVIDIA did. It's speaking the NVIDIA protocol, which kind of makes sense because AMD wants to plug into existing stuff. And in fact, everything looks like it's NCCL. And I'm just going to assume that it's essentially just an implementation of NVIDIA stuff. And I'm going to move along from there. MI Vision X. This, no, that's not what I want. I want MI Graph X. This should be something about building up computation graphs. In fact, let's look at some examples. Diffusion, maybe? NLP? Transformers. I don't want to get too fancy. Well, why not? Let's look at transformers. How about Llama 2? What? I don't know if I can look at an IPython notebook here. How about textgen.py? Yeah, that's totally true. Thanks, Fiction. All right, so 2MGX. Okay, so we've got some model. Then we're going to load an MGX model. We're going to call llama 2MGX load MGX model, passing in some dictionary that looks like a configuration dictionary, such as like input IDs, attention mask, which is just like a, I guess, what? Attention mask is just a list with two elements, I think, from the elements 1 and max sequence length. Initially, I thought it was a sequence, but it doesn't seem to be. And then we're going to llama tokenizer from pre-trained model. So what is MGX doing here? We've got llama 2 MGX. And this is just calling some function because the llama 2 MGX is the name of this class. We're calling load MGX model, which is here. It's a static method. And we've got this at measure thing. I'm guessing that's to instruct it to measure something like loading time. And where's MGX? MGX is here. For model, we're going to call MGX load, whatever the model is. We've got some MXR suffix. And here we've got MGX parse ON and X. I don't know what ON and X is, but it's maybe some other format. So I'm guessing that maybe this looks a little bit like, it looks a little bit like something like TensorFlow or JAX, where these models are kind of like a pickled or serialized bunch of tensors, essentially bags of bits, groups of vectors, and that this is just some like AMD specific format that either competes with those or is more general than them or more specific than them. But that's kind of what it feels like. So let's see if we can verify or not verify that. First of all, let's just grab this. Let's just take some of these suffixes like MGX format or ON and X format. MGX format was specifically created for Rise of Nations. think that's a different MGX format. Knowledge is power. MicroGraphX. Nope. I guess is maybe AMD specific. I don't know. We do have ON and X. ON and X is an open format to represent machine learning models. Is a common set of operators, building blocks, blah, 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 blah. So it's a format to save your models in. I wonder if like JAX will export to ON and X. A user-friendly toolchain that enables the seamless execution of something, something, something. Okay, so this is some third party. No, it's not third party. It's Google. So this is some JAX thing that will execute ON and X models. It'll convert them to JAX. Okay, so this does seem to be some like model thingamajiggy. What else do we have here? Actually, let's just look up GraphX. MI GraphX. Graph Inference Engine, which accelerates machine learning model inference. I feel like there's probably more to it, but I don't really understand. Did it say specifically inference? Where was that? Model inference. Okay, so given the description, I'm guessing that the idea here is that as opposed to something like JAX, JAX has to compile to, I don't know what it does. Maybe it does I think it uses XLA, which compiles down to some general device independent machine codey stuff. I think it's an LLVM, like middle layer or something, and then maybe LLVM compiles it to AMD ROCm. I'm guessing that this MI GraphX stuff is more tuned specifically to AMD hardware without going through the kind of middle layer approach or something along those lines. Eliminate convert, eliminate data type, floating point to double, fuse concat, fuse pointwise. Let's just look quickly at fuse pointwise. We've got dead code elimination, eliminate identity. Oh no. I see some stuff about scalars and broadcasting and multi-broadcasting. So I think we're a little bit closer to the machine execution than what? Than the Python module? I don't know. But this is at least looking like some of this. These are all terms that we've seen when dealing with like tensor-like data, pandas, R, NumPy, that sort of stuff, TensorFlow and whatnot. And I think that that's basically what we're doing. But let's verify with, I guess, Gemini. What is AMD and how is it different from things like TensorFlow or JAX? Just to give Gemini some points of comparison. So GraphX is a graph compiler specifically designed to accelerate machine learning inference on AMD hardware. So it's inference specific. I don't really think I understand. So in inference, you have a pre-trained model. So the model never changes. And you're just executing it over new vectors. So you don't have to deal with things like gradients or optimization. So I guess that is a sufficiently different problem, and you're mainly doing like sampling. So it does make sense that there's computationally different. Its key role is it optimizes the execution of pre-trained models by graph transformations. It reorganizes the computational graph, the sequence of operations in the model, for better performance. And it has hardware-specific optimizations. It tailors the execution to the unique architecture of AMD GPUs and CPUs. And it supports various model formats. Okay, whereas TensorFlow and JAX are broader in scope. Those are libraries for kind of moving tensors and data around. Okay, so this makes sense. This is taking an existing model, performing graph operations on it, and much less general. And by being more specific, it can optimize more. And I think that's good enough for me. I think I'm tired enough. And eventually, when you look at enough source code for too long, your brain starts to get mushy. And I think that's where I am now. And maybe that's where you are now. I don't know. But I do know, I'm so glad that you stopped by. I'm so glad. A big thanks to everyone in the chat. You guys have been great. And that is at least a little bit of the AMD ROCm platform. I'll be back, I think, next week. And I might dig more into some of this GPU stuff. I might do something else. And then later in the month, we will have the usual user or rather viewer requested stream. And Koorosh is asking, when do I usually stream? I usually stream on Mondays around 10 a.m. Eastern, which is the time I started today, modulo getting a little bit of a late start. Thanks. I appreciate that. Fiction is saying it was a pretty cool and chill stream. I really appreciate that. But I don't know if I'll keep doing the current time. I might. So I have another thing in the mornings currently, and I don't know. I don't know enough about that. So I may stream later on Mondays, but that remains to be seen. I'll plan on. Join the Discord, and that's where I'll give updates. My schedule has been crazy the past couple of weeks. Crazy isn't unpredictable, so I'd like to get that pinned down more in the next few weeks, but I have to do a fair bit of travel, so we'll see how that goes. But I'm going to plan on doing Monday. It might be more like 3 or 4 p.m. on Monday for a few weeks, but we'll see. I know that's late for a lot of folks who, for example, live in on the other side of the world, but that's what we got to do for now, I think. And with that, thanks again for watching. Join the Discord, become a patron, and all that stuff.